students. I am Santosh Megwade and I will be the instructor of your analog and digital electronics laboratory. So, as you know that we have already gone through the theory part of analog and digital electronics lab theory, in which the laboratory code will be 18 CSL 37. In this lab, the outcomes that we are expecting from the students are the student must be well known about, should be aware about electronic devices like cathode ray oscilloscopes, signal generators, digital trainer kit, multimeters, and component like resistors, capacitors, op-amp, and integrated circuits. Then student must able to design and construct various combinational logic circuits. Student should able to demonstrate and test various types of counters and registers using flip-flops. And finally, students will be able to simulate analog and digital circuits and implement the ALU. These are the outcomes that we are expecting. And in today's session, I will do the simulation part. Let me go to the syllabus, number of experiments that you have in your syllabus. You can see total 9 experiments are there for yours in this third semester AD lab syllabus. Okay, so within that you can see the first 3 experiments are related to the analog part and remaining 6 experiments related to the logical part, okay, or logical design part. So here, so with respect to this 3 experiments, that is the analog part, within that you can see it consists of hardware as well as software. Okay, that is nothing but here we will do the hardware experiment, and along with that we will use some simulator also. Fine, that is with respect to this analog part. The same thing we will go for this remaining 6 part also, 6 experiments also. There also we will do this hardware part, and along with that we will use a different type of simulator. Okay, so starting 3 experiments are having different simulator, and remaining 6 experiments are having the different simulators. And in today's lab, we will see with respect to simulation for the first experiment, that is design an astable multivibrator circuit for 3 cases of duty cycle, that is equal to 50%, less than 50%, and greater than 50%, by using the 555 timer IC, right? And we will simulate the same for any one of the cycles. Okay, 1 minute. Fine. So here we will first go through the first experiment. As you already gone through the definition for a multivibrator, and you have seen the types of multivibrator. Those were astable, monostable, and bistable multivibrators. Fine. So here in this lab, we have experiment based upon the astable or free running multivibrator using 555 IC. See, before performing any experiment, we have to design the circuit, and we can able to design the circuit based upon the formulas, based upon the equations, and we will perform some set of calculations on them by taking some of the values as an assumption. So here you can see we will use the time period of 1 millisecond, and we know that the t is equals to 1 by f, so which means that our frequency will become 1 kilohertz. We know that the total time period t is nothing but a high time plus low time, and the equation for low time is 0.693 into Rp, or you can say R2 into C. Okay, once you rearrange this RP, this equation, okay, you can able to identify the RB or R2 values. Similarly, for the high time, we have equation 0.693 into R1, you can say RA or R1 plus RB or R2 into C. Then again rearrange the equation so that you will get this particular equation, so that you can able to compute the resistance of R1 or RA. So you will use this equation number 1 and equation number 2 to calculate the RA resistance and RB resistance, or R1 resistance and R2 resistance respectively. So as in the syllabus it is mentioned that we have to verify for 3 cases, that is for the duty cycle greater than 50%, equal to 50% and less than 50%. So for the first case, we will take duty cycle equals to 75%, means greater than 50%. So once you represent this one in the floating values, okay, it will become 0.75, and we will assume the frequency of 1 kilohertz. Now apply the equations. T equals to 1 by f means frequency will time period will become 1 millisecond, right? So TH plus TL equals to 1 millisecond. So duty cycle is nothing but high time divided by total time period. Okay, so that is equals to 0.75. So once you apply the values, that is T high. Okay, that is nothing but here. That we don't know how much it is, but we know that duty cycle is 0.75 and total time period that will be 1 millisecond. So if we rearrange the equation, we will get high time will be 0.75 millisecond, right? So that will be the on state. That will be our on state, and TL, that will be the off state of 0.25 millisecond, right? So our on state only represents that the duty cycle. Fine. So later we will assume some capacitance value for capacitor C of 0.1 microfarad. Okay, and this value will be substituted in that equation 1 and 2, so that we will get the resistance value of RA or R1 of 6.8 kilo ohm and RB or R2 of resistance value 3.3 kilo ohm. Okay, so this is applicable, okay, only when you have duty cycle greater than 50%. At that time we will go for this R1 and R2 resistance value. The next one, case 2. In the case 2, again we will keep the same frequency, but the duty cycle will be less than 50%. So again we will use the same equations, we will apply the same things to that duty cycle, right? And we can able to calculate the high time and low time. Again we will assume the capacitance of the capacitor 0.1 microfarad, applying that one into the equation 1 and 2. Okay, so we will get a new resistance value of R1 and R2, or you can say RA and RB, of 8.6 kilo ohm each. Okay. The next one, case 3, that is a duty cycle equal to 50%. Apply the same thing to that equation 1 and 2. Okay, and capacitance value will be remain as it is, 0.1 microfarad. Okay, so you will get the new resistance value of 7.2 kilo ohm for R1 and R2 respectively, right? This is how we will design. Now next one, as you already gone through the triple phi timer pin diagram, okay, let's have a quick glance on it. Triple phi timer is consist of it is a 8-pin leg, in which the first pin it is a ground, second is trigger, third one is output, fourth one is reset, fifth one is control voltage, sixth one is threshold, seventh is discharge, and finally eighth one will be power supply, that is plus VCC. And beside to this pin diagram, we can able to see the circuit diagram, right? So we can see that here R1 and R2 resistors will be kept, and based upon our duty cycle we will apply that resistance values. And here you can see the capacitor C1 of value 0.1 microfarad. Okay, this is our capacitor voltage. Okay, and that voltage is going to drive this Astable multivibrator, and based upon this charging and discharging of the capacitor, Okay, that signal will be fed to this Astable multivibrator, and in the output side we can able to see the square wave waveform. Okay, square wave output. Right, and here we can see one more capacitor we have used. That capacitor we call it as a bypass capacitor, which is of having size 0.01 microfarad. Okay, so this bypass capacitor is going to remove all the AC signals which are present in this circuit. Okay, because AC signal will destroy it is going to disturb the DC signal, right? Because anyhow here we are applying the plus VCC means completely DC voltage. So apart from that, a kind of some little bit amount of AC voltage will be there. Okay, AC signals will be there. Okay, so to avoid that kind of noise, we will bypass all the AC signal through the capacitor, and everything will be grounded, so that we can only see the DC voltage in this circuit. Right, for this we are going to use this bypass capacitor C2. Fine. Now, as I said that in this video, I will demonstrate you the simulation part, and this is the one of the look of your simulation, okay, of 555 based Astable multivibrator. Okay, you can see here I have used a common ground. Okay, common ground. Okay, so it is not necessary that you can use only common ground. Okay, you can go for the multiple grounds also, but only it is applicable in the software side. But in the hardware, you have to maintain a common ground, right? Okay, so this is the circuit diagram that we are going to use to demonstrate, okay, to simulate our 555 timer based Astable multivibrator. So now let me switch to the software side, that is Multisim 11.0. Let me click on this. It will take some time. So here I am using NI based companies. Okay, that is a product of National Instruments. Okay, the product name is Multisim, version is 11.0. It is initializing all its commands. It will take some time. This multisim is only applicable for all those 3 experiments, starting 3 experiments. Fine. So once your multisim is open the window, you can see that there is a white sheet. This sheet or this place we call it as a design space or design worksheet, in which we will mount our circuits. We are going to mount our circuit, right? Means we are going to place all the resistors, timers, okay, function generators, okay, power supplies, everything we are going to put it on this workspace. Fine. But before doing the operation, it is a better thing to save the file. So first save as, let me save it as, anyhow I am doing on Astable, so Astable, okay, I am going to save this. Yes, now you can see in your left side of the window, okay, so Astable 555, that is the name of it. Now if I go according to that figure, okay, you can see what I need one power supply, one timer of 555, and next 2 capacitors and 2 resistors, and one oscilloscope, okay, to read the output. Okay, and you can either use a single ground, or you can go for the multiple grounds. Okay, there is no problem with respect to software side. So let me switch to the software part. Now what is the first one? First I have to keep the basic part. Okay, so let me first keep the 555 timer. Okay, you can see on the top left, you can see whenever I place the mouse cursor, it is going to show me that place source, place basic, place diode, okay, like that, some kind of component is going to show me. Okay, so what I am going to do here, I will select any one from here, okay, which is a shortcut way. Otherwise I can go to the place, okay, go to the place icon and select the component, right? And after that you can see here select the component. Within that, you have a database called a master database, which should be always present. Next one, what type of components that you are going to select. Okay, so here first I am going to select the triple for timer. For that, I will go to basic, and in the basic I will go to the rated virtual, and in the rated virtual you can see that I have a component called 555 timer rated. Okay, this is the component that I am going to select. Click OK, and I am going to place on this sheet. Okay, center of the sheet. You can see that whenever I move the cursor, okay, depends upon the movement of the cursor, even the component is also moving. Means I'm not at all mounted this one on this sheet. Okay, once I click, okay, that will be mounted. After mounted, you can see that again the select component window is going to pop up. Means it is asking to the user that do you want one more component? Okay, if it is, then you can go ahead. If not, just close it. Okay, so the first component has been placed. So anyhow, later I'm doing the operation, I will select this text so that I can keep it aside. Okay, it should not disturb my circuit design. Now you have VCC of pin number 8, then reset of pin number 4, then discharge of pin number 7, then we have threshold of pin number 6, then trigger of pin number 2, and control voltage of pin number 5, ground of pin number 1, and output of pin number 3. Right, once I am done with this, what is my next thing? Okay, so I have to place the resistors, right? So for that, again I will go to the place, okay, component, and within that I will go for, anyhow I am there in the basic only, basic group. You can see in this family resistor will be there. So in this resistor I will select, either I can go for that particular, okay, means here first I am going to do with the first case, that is a duty cycle of 75%. Okay, so for that our resistance value R1 will be 6.8 kilo ohm and R2 will be 3.3 kilo ohm, right? So either I should go for that 6.8 kilo ohm like this. Okay, yes, I got that 6.8 kilo ohm. Okay, and anyhow you can see that the particular component is attached to that cursor. Okay, but I don't want to keep this resistor in this in a vertical way. As you see that in the figure, it is placed in a vertical way, right? So I will use Control R to rotate that. Fine. So I am going to place this resistor over here. Fine. Then next, let me select one more. Okay, that is of 3.3 kilo ohm. Assume that I will use the same thing, right? So it is asking me that do you want one more resistor? I can go for either 3.3k. Okay, 3.3k. Where is 3.3k is there here. Select OK, and in the same order I am going to keep it like this, rotating, and in the same order you can see the dotted lines. In this order only I am going to keep it like this. Right, again it is asking, no, I don't want further, close it. Okay, or otherwise if you want to change the resistance value, what you can do, just double click on this 6.8, you will get 6.8k, and if you want you can change the value also. By default it will take everything in terms of ohm only. If you don't mention k, it will become 6.8 ohm. If you mention k, okay, it will become kilo ohm, that is m, okay, mega ohm, okay, similarly g, giga ohm, like that. Okay, 6.8k. Right, the next one is, what is the next one? Next one is I have to keep the capacitor, okay, of 0.1 microfarad. So for that again I will go to the place component. Okay, you can see here capacitor. Within the basic family we have a capacitor. Next you can go and search 0.1 microfarad. Yes, it is present over here. Select it. Okay, again you can see that it is showing in a horizontal way. Use the Control R keep it in the vertical order, again in the same line only. Again it is asking the capacitor. Yes, I want the capacitor, but here I am not going to use this type of capacitor. Okay, I am going to use a different type of capacitor. Okay, that is nothing but capacitor only. Okay, but it will be a electrolyte capacitor. Okay, it is a electrolyte capacitors. Okay, so cap underscore electrolyte. Okay, so in that I am going to select the value of 0.01 microfarad. Okay, if you are feeling that okay, it is not available for me, select any one randomly, click OK, and and place it like this. Okay, place it like this. I'm just going according to that figure, okay, so that you can understand. I don't want any further, I will close it. But I want to change this one. What I have to do? Just double click on this 4.7 millifarad and convert this one into 0.01. U means it will be taken as micro. Okay, so next click OK. You can see that the value has been changed. See, this capacitor is different. C1 is used for charging and discharging, and this capacitor C2 will be used to bypass the AC signals, okay, from the circuit. Fine. The next one. What is the next one? Next one, I have to keep the power supply, right, of 10 volt. Now again go to the place component. Now you can see that I am there in the basic. Now I have to go to the source because power source. So go to source, and in that I am applying the DC voltage, right? So for that, power source, DC power. Okay, DC power will be taken. So select OK. Okay, and you can see that this power supply is attached to this mouse cursor, right? But we know that, I hope you studied in your physics also, with respect to DC power supply, in a symbolical way, this small terminal, small line, small horizontal line indicates it is a negative, and big vertical line indicates it is a positive, right? So here this VCC should get the positive, but here it is pointing to the negative, right? So I have to go for rotation. Once I rotate, I can keep it like this. Okay, it is still asking, I don't want any lows. And here we have applied off volt 10 volt. So double click and change the value to 10 volt and click OK. Right, now you can see that I can able to give the positive potential of V1 to this plus VCC. Right, what is the next one? Next one is I should have oscilloscope, right? Oscilloscope. In this oscilloscope I have two channels, that is channel A and channel B. So you just go to the right side of the window, okay, and there you can see multimeter, function generator, watt meter, and oscilloscope. Select on that oscilloscope and keep it over here. Okay, yes, fine. I hope you can able to see now clearly. Okay, now we can able to differentiate between this capacitor and this capacitor, because C1 capacitor does not have plus and minus, but the electrolyte capacitor will have plus and minus, right? Next one is I have to use the grounds. For the grounds, what I have to do? Go to place again, select the component, and you can see within the power source only you can see ground. Okay, select the ground, click OK. One ground I am going to keep it over here. Again I want grounds. Another ground will be kept over here. Okay. For the simplification purpose I am going for the multiple grounds. Okay, and next one just below to the ground I am going to keep one more ground. Next, for this channel A, it's negative. Okay, I am placing one ground, and for channel B, it's negative. You can see plus and minus symbol will be there. Okay, I am only interested with the positive, not the negative. And next one more for this positive plus VCC. Right. Once I'm done with these things, okay, I don't need any further thing. Fine. So this is the overall component that I want to place and I have placed. The next one is I have to join everything. Now first of all, ground is connected with the ground. Fine, you can see the kind of red line. Okay, means it is connected. It's a kind of wire. And from this part VCC to this one, I have connected. And similarly, I will extend like this. Okay, again I will click and I will take the turn. Right. Next one, here this ground is connected to the negative of the channel A and this ground is connected to negative of the channel B. Fine. Next one, output is taken from channel A. Okay, you can see that it is taking some curve. Okay, I can take up to here and later I can go to what? Okay, let me take one more time. Okay, otherwise I can go in this way and I can connect like this. Okay, so output is taken from, it's taken in channel A. Okay, next one, here this capacitor is connected to ground, this capacitor is connected to ground, and as we have seen in the figure that capacitor resistors R1 and R2 both are connected, right? So for that, again C1 to R2, R2 to R1. Fine. Pin number 5, right? So control voltage, capacitor to control voltage. Here 2 can extend like this, it will take the turn, then you can see it is connected. Now next one is you can see here this trigger, okay, and threshold both are connected. Both are connected means pin number 6 and pin number 2 are connected, and that will be connected to in between R2 and capacitors, right? So for that, what I have to do, I will take the threshold, okay, I will extend like this and I will connect it between the R2 and C1. Okay, for this I will connect with the threshold also, right? Not threshold, trigger. Okay, so pin number 6 threshold is connected with the pin number 2 trigger, right? That is what we can observe in this figure. Okay, otherwise you can just refer this figure also. Okay, both are same only. See, pin number 2 and pin number 6 are both are connected between the R2 and C1, right? Next one, between R2 and R1 we will connect the pin number 7, that is discharge. Let me go here. Discharge is here between R1 and R2, so it will be connected like this. Okay, so pin number 7 is connected between the R1 and R2. Next one. Next, what we can see here, pin number 8 and pin number 4 both are connected to the plus VCC. Okay, so anyhow VCC is pin number 8, that is connected to potential, right? So again this one 4, pin number 4 is also connected to same positive potential, and this R1 is also connected to pin number 4 and 8, that is VCC and preset. Fine. So this is all about the connection. Okay, once the connection is been done, okay, one more is remaining, that is nothing but we have to read, okay, the capacitor charging and discharging. For that I will use channel B. Channel B, I will grab like this wire, and I will connect it to this part, because anyhow it is connected to between R2 and C1, right? So I will connect over here or connect it over here. Okay, it doesn't make any differences. Okay, for your understanding purpose, let me connect here only. Okay, so Channel A is used to read the output waveform, okay, and channel B is used to read the input waveform. Okay, next one, what you have to do, you have to save, right? So I will save the file. File has been saved. Next one, you can see here kind of a run or resume simulation or shortcut key F5 will be there. Click on it. Okay, you can't see anything over here. Okay, so to read the output, but you can see in the left side the triangle is blinking. Okay, means something simulation is happening, something execution is happening. So to see the output, double click on this oscilloscope. You can able to see the output. You can able to see the output, right? And here you can see that. Let me stop this. Okay, waveform. Okay, I've stopped. Next, you can see it is for the 1 millisecond per divisions are there. Okay, so means here this x-axis is nothing but the time. X-axis is nothing but the time, whereas y-axis is nothing but the voltage. Okay, y-axis is the voltage and x-axis is the time period. We have taken that our frequency is 1 kilohertz, so our time period will become 1 millisecond. So for that I should go for 1 millisecond, 1 millisecond per division, right? Fine. And here you can see that it is of, let me make it somewhat bigger so that you will be able to see. Right. So let me, okay, 1 millisecond, okay, means one complete clock cycle. Okay, so for reading purpose I will go again somewhat smaller values, right? So let me go for 0.5 millisecond per division. Per division means each and every x-axis, this particular block, one block with respect to x-axis is equal to 0.5 millisecond. Okay, whenever I change here, based upon that its meaning will also get changed. If I say 1 millisecond per division, so per division will become of having 1 millisecond, okay, with respect to x-axis. Similarly, you can see the channel A, okay, channel A is nothing but here the square wave output, okay, and channel B, that is nothing but the charging and discharging, right? So here both are of having 5 volt per divisions, okay. So let me go for this one only, right? Now next one I have to read the values. Fine. So let me go to the table. Okay, theoretically we have assumed that 75%, right? So I will take it as 75% over here. Time period. What is the time period here? Okay, so to calculate the time period, what you have to do, you have to use the channels here. Okay, so not channels, time period, or I can say timelines. Okay, so this is the timeline 2 and this is the timeline 1. Okay, so one complete clock cycle means, let me select, I will keep this timeline exactly on this particular line. Okay, you can see that now color has been changed, right? Okay, so it is a positive cycle and this is the negative cycle. Okay, now you can see that. Okay, let me take off the move. It is almost there only. Okay, so it, okay, fine. So we can see here T2 minus T1. T2 minus T1 means the timeline T2 minus T1. Okay, so that is nothing but here we can see 944.0.56 microsecond means 0.94 millisecond. Okay, so we have taken the frequency of, we have taken as frequency of 1 kilohertz. So time period will be 1 millisecond. I am getting here 0.94 millisecond, which is almost near, right? That is the thing that I have to note over here. Okay, time period is 0.94 millisecond. Next one, frequency. Convert that one into frequency, 1 by 0.94 millisecond. Okay. Next one, pulse width. pulse width is nothing but complete on state. One complete on state. Okay. So let me just complete one on state. Let me keep it like this. Okay, one complete on state means complete one positive cycle only I am going to consider. Negative cycle I don't consider. Okay, so now what is the time period now? Okay, T2 minus T1. Okay, so it is nothing but 704.296 microsecond means 0.70 millisecond. Okay, so approximately 70% of the duty cycle is nothing but it is a that is the duty cycle. 70% is the duty cycle. What is our assumption? Okay, we have taken 70%, 75%, and we got here 70%. Okay, which is greater than 50%. Okay, almost same. The next one, pulse width we have calculated, right? Next one, UTP. Okay, UTP and LTP. I hope you have gone through in your subject also. Okay, there is an intersection. Okay, upper trip point and lower trip point. So for this, either you can go for channel 1 or channel 2. Okay, you can keep it like this. Okay, I will keep it like this over here. Okay, fine, almost there. Okay, now T1, based upon the T1, okay, that is a timeline 1. Okay, you can see that there channel A. Okay, channel A is nothing but that is square wave, right? So but here we will see the intersection point here with that is nothing but channel charging and discharging of the capacitor, that is taken from channel number B, channel P. What is the voltage here? That is 3.364, right? 3.364 volt. That is the thing, but you just calculate 1/3 into VCC, that is 1/3 into 10. Okay, 10 is our VCC, right? So how much you will get? You will get nearly 3.36, okay, or 3.33. Okay, so almost we are getting the same voltage, right? And similarly for calculating the upper trip point UTP, I am referring to the timeline 2. Okay, so that is the thing, but again we are getting with respect to channel B. Okay, so for T2 it is 6.663. Okay, 6.663 means again that is 2/3 of VCC. Okay, 2/3 of VCC, 2/3 into 10, so we will get 6.66, right? So that is the UTP and LTP values. Fine, so this is how we can able to calculate this duty cycle, UTP, LTPs, okay, time period for this given this computed waveform, okay, or this generated waveform. Now next one is, that is all about case 1. Okay, now next one is case 2. Okay, before going to the case 2, okay, let me go for the case 3. Case 3 is talks about in which, okay, let me go for the case 2 only. Okay, so here I have to just rearrange. I'm going to rearrange. So here it will become, okay, sorry, it is saying that the simulation is running, we can't change. So before that I have to stop it. Okay, before doing any modification to the value, first I should stop that one, stop the simulation. Later I can go for the updation. So I will keep it as 3.3 kilo. Next, here I am going to keep it as 6.8 kilo. 8 kilo means just I am changing the values, that's all. Okay, I'm just changing the values, means now R1 value is less than the R2 value. Fine. Next, I will save that one. Next, I will run the simulation. Double click. Okay, double click on the oscilloscope. Okay, you can see that it is producing the output. Fine. I think we have taken not 3.3 and 6.8. We have taken 8.6 and 5.7. Okay, that is my bad. Okay, I have taken very different values. So it is 8.6, 8.6K, and another one is 5.7K. Okay. Now save it and run the simulation. Double click. Again, I have taken all values. I think it is also 8.6. Okay, so for such kind of situations, okay, what we have to do, we will introduce one diode. Okay, so first let me stop this one and again go to the place. See, this diode concept will come only for the second and third case. So component, go to the basic or diodes. Okay, go to the diodes. Okay, and here you can see diodes will be there. 1N466 select this one and rotate, keep parallel to this R2, and you can see the face is downward, and connect this one between this R2, okay, parallel to this R2. Fine. Just save this, run it, double click. Okay. Okay, I got the third case, that is equal to 50%. Okay, so let me stop this one. Okay, either because both the resistance values are same. Okay, 8.6, I revise case 3, right? Case 3. Double click on this. Okay, so we actually did 7.2K. This is also 7.2K. Anyhow, both are, but we have done some calculations. We will go according to that. Save it. Run it. Double click. Okay. You can see that starting it took some time. Okay, after that it will become normal. Fine. So because of the diode, some of the waveforms will go like this. Okay, not a problem. So anyhow, 500 means 0.5 millisecond per division and 5 volt per divisions for the y-axis. Again, use this timelines. You can see the timeline 2. Okay, you can see the color has been changed. Next one more. Positive clock cycle. Negative. You can see that T2 minus T1 will be 1 millisecond, right? Fine. The next one, what is the duty cycle? That is high state. You can see that it is 55.9, okay, 0.441 means almost 56, okay, 0.56 millisecond means we are getting approximately somewhat 56% of duty cycle, right? And next we can go for the UTP and LTP. Here one you can able to see that for channel timeline 1 with respect to channel B, you can see 3.3, that is 1/3 of VCC, that is 3.3, and for T2, time period T2, again channel B, we will get 6.6, that is 2/3 of VCC, right? So this is about case 3. Fine. Next. The last one is a case 2. In the case 2, we will use we will change the values. It is here. It is here. We will use 5. Let me save this. Let me execute this. We run this. Okay. No, this is wrong. Fine. Yes. From 6.8K. A little bit confused. This. Only for the third case. Use that. Okay, so let me stop this and let me take any one of the waveform. Okay, so this is a, you can see here it is somewhat big because the charging, initially charging will take some time. Okay, so because of that. And next one, we will calculate the time period. For the time period, okay, one complete clock cycle, complete time period. Okay, so it is a 1 point. Okay, I took so much more. Okay, it is a 1.184 millisecond. Okay, near to 1 millisecond only. The next one, the UTP and LTP values are again same only. It is a 3.3 and 6.649 UTP and LTP values, and total time period will be around is almost same, only 70%. Okay, so in the hardware we will do any one of that case. Okay, but in the simulation, okay, it is nearly 7. Okay, so 7 means nearly 70%. Okay. So, so this is about case 1, case 2 and case 3. Okay, we got accurate one for the case 1 and case 3. Okay, but case 3, okay, case 2, a bit we didn't get that much accurate one. Okay, so this is about the simulation. I hope you understood the concept. I hope you understood how to plot, how to draw this circuit, how to select the components. Fine, right? And in the next session, we will see the hardware part of the Astable multivibrator. So here I am going to stop the session. Thanks for the listening. Have a great day.